Welcome to this explainer. Okay, so today we're going to dive deep into the fundamental physics of our universe. We're taking a journey far, far beyond what the human eye can see and going straight inside the very building blocks of matter. I promise you, by the time we finish up here, you're going to look at the physical world around you in a completely different way. Let's get into it. Now, I want you to really think about this for a second, because it's one of the oldest thought experiments in human history. If you take any physical object, like a table, a distant star, or even a microscopic bacterium, and you just continuously divide it in half, over and over, what's the ultimate stopping point, right? Does matter just divide infinitely, or you eventually hit some sort of fundamental floor?
Well, way back in the 5th century BCE, the Greek philosopher Democritus proposed that matter ultimately reduces down to these tiny, uncuttable particles. He called them atoms, which literally translates to undividable. And for a massive stretch of human history, that was just the accepted truth. But, as we're about to see, the name atom is actually incredibly ironic.
Fast forward to the modern scientific era, and we realize atomic scales are far too small for any ordinary microscope. Scientists couldn't just look at an atom. They had to play detective to deduce its structure. They figured out it has a tiny, dense central core surrounded by revolving negatively charged electrons. But that raises a huge question. How exactly do you prove a central core exists when you literally can't even see it?
Part 1. The Gold Foil Shock.
So, scientists Geiger and Marsden engineered an absolutely brilliant workaround to essentially see inside the atom. They took an incredibly thin sheet of gold foil, placed it inside a vacuum, and surrounded the whole thing with a rotating fluorescent detector screen. Then, they bombarded that foil with a continuous beam of heavy, positively charged alpha particles. The assumption going in was pretty simple. These heavy particles are just going to punch straight through the foil, no problem.
But the actual results? They completely defied classical expectations. While it's true that most of the alpha particles did pass straight through, a small fraction of them behaved totally erratically, deflecting off at these really sharp angles. And even more shocking, literally, they could hardly believe it, a few were repelled so violently they bounced nearly 180 degrees straight backward.
Ernest Rutherford looked at these erratic deflections and realized something huge. The atom isn't a solid mass at all. It is mostly just empty space. Those particles bouncing backward, they had struck a central positively charged core, the nucleus. To really put that massive scale into perspective for you, if the entire atom were the size of a giant football stadium, that incredibly dense nucleus in the center would be the size of a single pea.
Part 2. Inside the dense nucleus.
Okay, let's zoom right into that tiny pea-sized core. Inside, we find two totally different heavy elemental particles. You've got the positively charged proton and the neutral, uncharged neutron. And what's really remarkable here is the sheer mass disparity. While protons and neutrons share a relative mass of 1, those negatively charged electrons orbiting way out in the empty space, they are incredibly light. We're talking roughly 1/2000th the weight of a single proton.
Part 3. Quarks, the ultimate foundation.
So we've broken the atom down, but let's push it even further. When we look incredibly closely inside a single proton or neutron, we discover that they aren't solid either. A proton is actually a compact bundle of even smaller, more fundamental subatomic particles called quarks. And these quarks don't just float around, they are bound incredibly tightly together in little clusters by strong nuclear forces. These forces are appropriately named gluons because, well, they literally act like the glue of the universe.
Part 4. Classifying the elements.
Now let's zoom all the way back out to the chemical level. What's absolutely fascinating is that an element's entire identity in the physical world boils down to just one simple metric, the proton count. The number of protons inside a nucleus is its atomic number. 6 protons? That makes carbon. 8? You've got oxygen. That single number dictates the entire material.
And to figure out the bulk of the atom's actual physical weight, we use the atomic mass. Since we know those orbiting electrons are practically weightless, we simply add together the heavy particles housed in the nucleus, the protons and the neutrons, and there's your mass.
You can really see the elegance of this mathematical classification when you look at the lightest elements. Hydrogen has just 1 proton and an atomic mass of 1. But add 1 proton and 2 neutrons, and you suddenly get helium with a mass of 4. Think about how profound that actually is. By simply adding microscopic protons or neutrons to a tiny, invisible core, a light, floating gas fundamentally transforms into a totally different material, like a solid metal such as lithium.
As we wrap up this explainer, I want to leave you with this seriously mind-bending reality of this subatomic world. We've established that everything, from massive planets to our very own bodies, is made of atoms. And we've learned from that ingenious gold foil experiment that an atom is primarily just empty space, a football stadium of pure void with a single P of mass right in the center. So, if we are made of atoms, and atoms are mostly empty space, does that mean we, and literally everything around us, are mostly made of nothing? I highly encourage you to ponder that the next time you confidently knock your knuckles on a solid wooden table. Thanks so much for exploring the invisible universe with me.